Okay. Well, hello. I'm Toby Burnett. I'm an emeritus professor at the University of Washington, and I've been working on the astrophysics project for some time. And even though I'm 10 years past becoming emeritus, as they say, I'm still working on it. And this opportunity came up, and I was sort of connected with Timothy, whom I'm now introducing, who had an interest in astronomy and had taken AP computer science. He's about to start his senior year in Tacoma, not so far away from me. But anyway, my project involved Python coding in a Jupyter environment and a bunch of some coding and even data visualization. Although for the wavelengths that I deal with, which are 100 millionth less than that of light, things are a little different, and you'll see from what he shows. So, Timothy?
Yeah, thank you. Ariel, would you mind sharing my presentation that I emailed you?
Sure.
Or should be in the Dropbox, maybe. If not, then I can always share.
I've got it.
Okay.
Okay. Here we go.
All right. So this is going to be my presentation about Fermi data variation. Next slide. So my project, I got to study data from the Fermi Gamma Ray Space Telescope. With this data, I got to learn about Python, and using that, I got to make ITOF projections using the galactic coordinate system to show variable gamma ray sources. The end goal of the project was to make a GIF to show these variable sources, and hopefully we could detect some new sources that haven't been discovered yet. Next slide. This is a slide about the Fermi Space Telescope. It was formerly known as GLAST, Gamma Ray Large Area Space Telescope. It was launched in 2008, meaning that it's been collecting data for 14 years. It had a goal of collecting high energy gamma ray sky data, and it has two main instruments. I mainly use data from the Large Area Telescope, the primary instrument on Fermi, which covers an energy range from about 50 mega electron volts to about 1 tera electron volt. It is a state-of-the-art high energy gamma ray telescope, or at least it was when it was created. And then there's also the gamma ray burst monitor, which provides spectral coverage of the gamma ray bursts, which extend from about 10 kilo electron volts to about 17-ish mega electron volts. Next slide. Okay, so this is an image of the gamma ray sky. I've labeled some consistent points here. This main area in the middle is the center of the Milky Way. And to the right of that, we have the Vela pulsar, Geminga, and the Crab pulsar. These are some of the more vibrant constant sources of the gamma ray sky. But there are also some other points that you see, which would be, these other flashes are AGN flares. And that big dot in the bottom left would be the, I spent a lot of time trying to figure out what it was, but it turned out to just be the sun. Next slide. So to give some background, pulsars are a highly magnetized rotating neutron star. They emit beams of electromagnetic radiation out of their magnetic poles as they rapidly rotate. This radiation can only be observed when the beam is facing or pointing towards the Earth, and they remain constant sources of gamma ray emission when we analyze this data. I've listed the three main ones I had in the previous slide here of the Vela pulsar, Crab nebula, and Geminga. Next slide. AGNs are another source that we oftentimes study or look at, which are active galactic nucleus or nuclei, a compact region at the center of galaxy, which is has a much higher than normal luminosity. The radiation is theorized to be formed from matter accretion by supermassive black holes. Now I've listed two different types here, a quasar as well as blazar. Quasar is a powerful type of AGN. It is most powerful actually. The one that I found most frequent and relevant was the optically violent variable quasars, which are considered a type of blazar as the jet points towards the observer, or in this case, Earth. Now, a blazar is an AGN with a jet that's pointed towards the observer, and the radiation is enhanced by relativistic beaming. You can see the main difference between quasars and blazars, or at least optically violent variable quasars, are oftentimes the actual angle of the beam or jet. In this case, that is the difference between these two images to the right. Next slide. These are three sources that I came across that were more major, more common in terms of talked about, if that makes sense. We have 3C273, which is the brightest quasar in at least the Earth sky, to the right there. And it was mainly, the last flare was around 2009 in September. Then I have 3C454.3, which was the brightest blazar gamma ray flare recorded with brightness twice that of Vela, the brightest pulsar. And this image is about from June 2014. And the last one I have here is 3C279, which was an optically violent variable quasar. And it is one of the brightest and most variable sources of gamma ray sky monitored by Fermi. And this one was from around June 2015. Next slide. So this is the process of how I actually get these images. First, we have a count map. The count map will show the counts of the photons over a specified time frame, which in my case is a month or 30 days. So every 30 days, I make a map using the count data. And then I also use an exposure map. The exposure map will show the total exposure, which would be the area multiplied by the time. The exposure is proportional to the counts. And so the more counts there are, the higher the exposure will be. And in the middle there, I include the code which I use to make these count and exposure maps. Next slide. This is the map which I use most, as this is a flux map. In order to get this, you take a count map and you divide it by the exposure map. And so I get a flux map, which will show us the more consistent or strong sources. So things that are more likely to actually be emission sources instead of just ended up being random gamma rays or particles here and there. I also include some code of how I end up getting the flux maps in the bottom left. Next slide. This right here is what the end project was of these flux maps. This shows all 14 years of Fermi's data on a monthly basis of the gamma ray sky. And all these flashing points that come and go, those are most likely blazars, or to be more specific, they are AGNs. But we can see that there are a lot of other points there which stay constant. Those are pulsars, which are, well, I mean, they're pulsing, so I feel like that's kind of a given part of that. Next slide. Now, I wanted to take this a step further because I talked to Toby about this, and when we talked about this, we discussed about how I could eventually get to a point where we might be able to locate new sources by taking data from the telescope or the public data set, and eventually use that to actually locate these sources. And so I thought the first step to get there would be by isolating the stronger sources. And so I went ahead and I took the flux over all 14 years as a comparison. And I would take a month and I would put it over the 14-year total average flux. And what this did is it would allow me to isolate all of the major variable sources. And you'll see that in the next slide. So this is a GIF of all of it's the same thing as the last GIF, except this is just isolating all of the sources that were major. And so we can see all these things here are things which are changing. All of these should be AGNs, I believe. And so what this is doing is it's saying that everything that is not constant throughout the 14 years is going to show up. And next slide. So how is this project significant? Well, this is a significant project because it has never been done before. I believe we have a lot of images of the gamma ray sky, but I don't believe it has ever been done across all 14 years of the data set. But it's also significant because from where I am now, I have the ability to hopefully end up being able to make a program to actually, as I said earlier, isolate and locate new sources of gamma emissions, and maybe even make it interactable, kind of like the FAVA tool that we currently have.
Hello. Before I start,
but I would like to thank my mentor, Toby Burnett, and the N3 program for giving me this opportunity. And I had a lot of fun, and I look forward to continuing my work with Toby Burnett in the future. And I guess just as one extra slide, I went ahead and included some of the variants of what I did in my project. All of these are trial and errors to try to make flares more apparent. Just thought it was kind of interesting. All right, thank you, and I look forward to continuing my work.
Thanks, Timothy. That was super cool. I really enjoyed that last slide. It's fun to see your process. So thanks for including that. Does anyone have any questions for Timothy? You can always ask them in the chat if you think of something later.
Timothy, did you end up having a source that was your favorite source of gamma rays?
That's kind of a difficult one because there's so many. I feel like I didn't include in the presentation, but BL Lacertae was an interesting one because especially with things that are more closer to the center of the galaxy along that middle axis, I feel like those ones are my favorites just because it's fascinating just to see something actually show in all of that like bright area. So I feel like anything mostly along that area is probably my favorite just because I love how you can tell how strong the source is because it stands out even amongst all of that, all of
the galactic background. Yeah, I think you're,
yeah.
No, I mean, that's pretty amazing because BLAC is actually obviously not in our galaxy. It's an entire other galaxy, right? So the fact that it can shine through our galaxy just shows how strong it is. Anyway, really, yeah. I love the maps.
Thank you.
I hope to see them at a Fermi conference in the future.